This is Sydney, CJ, and Solange here to present our project. Our central question is, what factors are involved in observing a star? There are many variables to be considered, like chemical composition, mass, and gravity. We decided to focus on the Doppler effect in light waves, called redshift and blue shift, and stellar rotation. These applications help astronomers understand more about our sun and stars in other solar systems.
The Doppler effect means the observed change in the wavelength and frequency of a wave as an object producing waves moves towards or away from an observer. For light waves, this change is considered a redshift or blue shift. When the object moves away from an observer, it's considered a redshift. When an object moves towards an observer, it's a blue shift. This concept was discovered by Edwin Hubble through his observation of distant galaxies. Understanding the visible light spectrum is important to understanding redshift and blue shift. At one end of the spectrum, there are waves longer wavelengths and smaller frequencies, which is where wavelengths sit. At the other end, wavelengths are shorter and the frequency is greater, where blue and violet wavelengths are. So if the observed wavelength becomes bigger, the observed waves shift towards the red end of the spectrum. Smaller observed wavelengths approach the blue end of the spectrum, redshift and blue shift. Although redshift and blue shift primarily occur due to the expansion of the universe, astronomers use redshift and blue shift to observe moving objects, like the rotation of galaxies, binary stars orbiting each other, or the movement of galaxies and clusters, as well as the movement of stars within our own galaxy. Because stars produce their own light and galaxies contain those stars, it's pretty easy to measure redshift and blue shift from their movement.
To measure this movement, we use the formula. The difference in wavelength is found by subtracting the wavelength at rest from the observed shifted wavelength. If there's a larger observed wavelength, the difference will be greater. If there's a larger wavelength at rest, the difference will be smaller. Finding the magnitude of the redshift or blue shift is found a different way, but including the same variables. Z, the magnitude of the shift, is equivalent to the difference in wavelength found in the first formula divided by the wavelength at rest. Larger rest wavelength means smaller magnitude of shift. Larger wavelength difference means larger magnitude of shift.
If a star is moving away from Earth quickly, the observed wavelength will be much longer than the wavelength at rest, producing a larger difference in wavelength and magnitude of shift. The opposite is true if it's moving towards Earth quickly.
Observing the rotation of a star is also a very helpful concept. Rotation is a circular movement of an object around a central axis. Rotation is evident in many everyday things, like a car tire or a spinning ball.
To calculate basic rotation rate, we use this formula. In this case, v is the tangential speed, or the rate at which an object moves in a circular path. R is the radius of the object's cycle, and the w is the rotational speed.
With the sun, rotation tracks the movement of the star and is included in its life cycle, from early molecular stages to death. The initial rotation of a star influences how the star will form, including its shape and later evolution. Rotation of stars can be optically observed through sunspots, as discovered by Galileo Galilei. As sunspots, cold, dark areas of the sun, move to the west across the surface of our sun, and move across the surfaces of other suns and stars. Stellar rotation is a star's angular motion around its axis. It's influenced by the star's initial angular momentum and other things like solar winds and magnetic fields. Because of the magnitude of which the observed object is at, the entire process of finding and evaluating stellar rotation becomes extremely complicated. To still be able to find stellar rotation, astronomers seek projected stellar rotation, which is the same idea but is more of the apparent rate of rotation considering the angle of inclination from a defined radius along the observer's line of sight.
The projected stellar rotation velocity formula is as follows. V sine I is the projected rotational velocity for a star, the velocity we observe in our line of sight. V equatorial is the true rotational velocity of the star. I is the inclination angle, which is the angle between a star's rotational axis and our line of sight. This formula can be used to determine the projected stellar rotation or our prospective star rotation, the true rotational velocity of the star, and the inclination angle.
There are multiple ways of applying the projected stellar rotation formula, like the Fourier transform, which uses the first zero of the Fourier power spectrum to find V sine I. There's also goodness of fit, which uses the different shapes of a broadened, rotational, and turbulent path to find the best fit of the spectral line for stellar rotation. Having accurate knowledge of this rotation is important to understanding a star's properties and its level of evolution.
Learning about rotation and how we observe it in space is important for a number of reasons. For one, we see rotation every single day, in wheels, carnival rides, and in the rotation of our own planet. And for another, we already know quite a bit about light waves and observation, but it works differently in space. Observing stars can help with understanding rotation, light waves, and how we see things in general. It also helps with understanding the life cycle of stars, what we can understand about them using these two concepts, and more about the universe with billions of these stars within it. Thank you.